Today we start the new topic, atomic spectra. In that, we explain the first article, the optical spectral series for doublet structure. Under that article, we explain these points. First, observed hydrogen fine structure. Second, spectral notations. And then we explain optical spectral series of a given elements. Now see what is hydrogen fine structure. For that, we have to considering here hydrogen, which shows the simplest spectra, since the hydrogen is one of the element in the periodic table whose atomic number is 1, means there is only one electron and its atomic mass is 1. Such a hydrogen shows the discrete spectral lines. Now how it get the discrete spectral lines? We draw the energy level diagram. Electron is in the ground state, means n equal to 1 is the ground state. Electron is in that state. If that electron gains some energy, it goes excited in the higher energy states, means n equal to 2, n equal to 3, n equal to 4 up to infinity, all are excited energy states. When electron can excite from higher energy level to lower energy level, it emits discrete spectral lines. In that, all that spectral lines which are observed in ultraviolet region, visible region as well as infrared region. Here we see for the transition n equal to 2 to n equal to 1, one of the spectral line we are observing here, that which come under the Lyman series, that is observed in ultraviolet region. The another transitions like n equal to 3 to n equal to 2, we get the Balmer series. In that Balmer series, the different spectral lines are seen here, that is H alpha, H beta and H gamma. All the lines are observed in the visible region. Now see here, such a Balmer series spectral lines which get the transition from n equal to 3 to n equal to 2, we get the H alpha line. N equal to 4 to n equal to 2, we get the H beta line, and n equal to 5 to n equal to 2, we get H gamma line. Such a spectral lines, now that explanation was given by, the theoretical explanation of the Balmer series was given by Neil Bohr. Again, the experimental analysis of the Balmer series was also shown by here Michelson. Before that, we see here for the Balmer series H alpha line, according to Bohr theory or the Schrödinger theory, when the transition can take place from n equal to 3 to n equal to 1, we get the H alpha line. That H alpha line is observed in the visible region, having the wavelength equal to 656.47 nanometer. Such a spectral line is observed by using high resolving power spectroscope. That experiment was done by the Michelson, and then he observed the single H alpha line is splitted into close doublet spectral lines whose separation is very small, of the order of 0.16016 nanometer. That explanation of the doublet fine structure shows the hydrogen shows the fine structure, and that explanation was given by the Sommerfeld by introducing this model of atom in which the electrons are moving in the elliptical orbits. It means for a given n value, there are number of subshells, and all these subshells are in elliptical in nature, means electron in that subshells is moving in elliptical path. Due to the elliptical nature of the subshells, the different orbits have different energy levels, and due to different energy levels, the transition when takes place from higher to lower energy level, it show close spectral lines. That means hydrogen atom shows a doublet fine structure. Such a concept we use in this topic for other elements whose configuration is same as here the hydrogen atom. Now see, before that we firstly explain what about the spectral notations. To explain the spectral notation, we mostly choose the alkali metals. Now these are the elements in the periodic table. Those come under the group first elements. All that elements which having the NS1 configuration means what? This group first elements like hydrogen, lithium, sodium, potassium. Now we see the configuration. Hydrogen, what is the configuration? 1s1 means there is only one electron. That electron we call valence electron or optical electron. Lithium, atomic number is 3 means what is the configuration? 1s2 2s1 means in the second shell, in that second shell there is subshell S subshell, and in that F subshell there is again one valence electron. That electron has configuration 2s1. Sodium, if we see the sodium, atomic number is 11. How we write the configuration? 1s2 2s2 2p6 3s1 means this valence electron configuration for the sodium is 3s1. Similarly, potassium 4s1. Hence all alkali metals have the configuration, valence electron configuration is ns1. Now we see what we have to find. What is the normal energy state of the alkali metal? For that we considering if the electron in the outermost orbit, that electron we call the valence electron or we call free electron. That free electron we write its energy state for all alkali metal, that we write N doublet S state. Now what is N doublet S state represent? We read as just like it is not N square S. We read N doublet S state. Now what the represent here? N, that is the prefix in that state. It represent the principal quantum number. That principal quantum number goes from n equal to 1, n equal to 2, n equal to 3 and so on. Means n equal to 1 means K shell, n equal to 2 K L shell, L equal to 3 M shell and so on. Now what the represent? Superscript 2. It represent the multiplicity of the state. The multiplicity of the state is written as 2s1 plus n. What is s here? S is the spin quantum number. And according to this wave mechanics, the magnitude of the spin quantum number for alkali metal, those having only one electron in their outermost orbit, its magnitude is, we have to take a S is half. Hence, that the multiplicity of each state, each normal energy state of the alkali metal, it is written as N doublet S state. For example, for the hydrogen, it is 1 doublet S state. For lithium, it is 2 doublet S state. For sodium, it is 3 doublet S state. Similarly, K, 4 doublet S state. These are the normal energy states of the alkali metal. Now we see here, as that electron, we can say, which is in the normal state, this electron we call free electron or valence electron. If that electron gain some energy, external energy, then it goes to higher permitted orbits. Now how it goes to higher permitted orbits? Now higher permitted orbits are S, P, D, F. These are the subshells. That subshells which correspond to L equal to 0, it corresponds to S. L equal to 1, it corresponds to P. L equal to 2 corresponds to D. L equal to 3 corresponds to F. Now these are the higher permitted orbits. Means as electron goes to higher permitted orbits like S, P, D, F for different n, then the corresponding energy states are, we write here, these are the capital capital S, capital P, capital D, capital F, etc. Now these are the corresponding energy states. These are the excited higher energy states. Which is the ground state? Ground state is N doublet S state. Or you write here, these are the ground state, and above the ground state all are excited energy states, and these excited energy states are denoted by the symbol capital S, capital P, capital D, capital F, etc. Now here we have to use Bohr theory, and according to the Bohr condition, we know that as the electron can transit from higher energy level to lower energy level. Now for example, if we write, this is the one of the higher energy level. Now this is the higher energy level and this is the lower energy level. If the electron transit from higher energy level to lower energy level, then what it emits? It emits the radiation, and that radiation has frequency equal to energy difference between the two states, means E higher minus E lower. Hence delta E, that equal to, we write delta E equal to h nu. See, according to the quantum condition, the energy difference between the two states, it gives the frequency of the emitted radiation. Now this experimental observation we note here. The Rydberg observed the alkali spectra of all elements. Then he observed that each element show 4 series of the spectral lines. That observation was done by Rydberg. Hence we write here the Rydberg series of the spectral lines. These are 4 series or the 4 groups of the spectral line. Now which is the first series? Sharp series. Second, principal series, that we indicate the name start from the first symbol, that is all are from the S state. Principal series, that series is the result of that series we start from all P states. Diffuse series, this is another group of the series he observed from the observation of the alkali spectra. This is the diffuse series, and from that diffuse series means that series is the wider as compared to the other one, therefore the name we write diffuse. Hence all series or the spectral lines which arise from D state. Similarly, that series also arise from all F states. Now we explain that how we get the different series of the spectral lines from each and every alkali elements whose configuration is N doublet S. Now this is the normal state of the alkali element. Now we write here one example. For sodium atom, we know that the sodium atom atomic number is 11. Therefore we write the configuration. Configuration is 1s2, 2s2, 2p6, 3s1. That the 3s1 is the one of the electron which is left in the outermost electron. That shell is not completed. Here this is the K shell. Here this is the L shell. K shell is completed, L shell is completed. Therefore this electron does not take any part in the transition process. These are the bound electron with the nucleus. Only the electron in the outermost orbit, that is the 3s1, that electron is valence electron. Such that valence electron is only responsible for the emission of the spectral line. That electron which always remains in its ground state. If that once the electron gains some energy from the external source, electron can goes to ground state to higher excited states. And which are the higher excited state? Above all states are excited state. Above 3s states all are excited state. For example, 3p, if we continue that configuration just like above ground state all are excited state. 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5D, and so on. These are all excited states. That excited states which represent, these are the excited states of the alkali metal. These are denoted by corresponding energy states represented by the capital symbols P, D, S, just like. Now, in that, how we get the Sharp series? Now, for explaining the transition spectral line, transition process and resulting spectral line under the Sharp series, hence we say that now which are the excited states? We know that above ground state all are excited states. Means if the electron goes from ground state to higher energy state, it does not remain in that energy states permanently. It come back again from higher to lower state. Hence, which are the higher states? All are higher. Excited states are the higher energy states. Now, in the under Sharp series, we get series of the spectral lines. Those are transition takes place from NS excited states to 3P lower fixed state. Now suppose we write here, this is the ground state, which is the next higher state 3P, next higher state 3D, next one is 4S. If we say all S states is correct, that is NS. It start from 3S, 4S, 5S, 6S, 7S and so on. But in that, which is the ground state 3S. Above ground state there is a 4S state. Hence we start from 4S, since electron goes from 3S to next 4S state. Now how we get? NS is the running state. NS is the running state. And that running state is taken as a from all 4S, 5S, 6S, 7S. The electron can transit from this state to lower state. Which is the lower? 4S below. 4S below lower state is 3P. Hence we write 3P is the lower state. Hence lower fixed state is keeping as a 3P. We cannot write here the lower state is 3D. Is correct. Now just write here nearest to that state. This is the 3P state. Hence N must be taken as a, should be greater than or equal to 4. Means N equal to 4, 5, 6 and so on. The resulting series becomes a Sharp series. Hence how we get the Sharp series? If the transition takes place from NS state, these are the running state, to fixed state. Fixed state is lower fixed state below 4S, which is the lower fixed state 3P. The resulting series becomes a Sharp series. Second, principal series. Now this is another series, principal series. Here also we write how the transition takes place. The transition takes place from all NP states. Means all NP states are acts as in here the running state. Which are the NP states? NP start from greater than or equal to 3. Means N equal to 3P. We cannot write here the 2P since this is a bound state. Excited state only we just take into consideration. N is greater than or equal to 3. Means N must be equal to 3, 4, 5, 6 and so on. Hence, the transition takes place from 3P, 4P, 5P, 6P, 7P and so on to the lowest fixed state. Fixed state nearer to that one is 3S. We cannot write go to the F. Since this principal state is, lower state is 3S and lower state ground state. Say here. That is the principal series. Similarly, diffuse series. Hence, how we get the diffuse series? Since these are the wider. Say here, these are the wide other than other spectral lines, and therefore it is we calculate the diffuse series. Diffuse series, we say which are the running state? All ND states. These are the running state. Means N should be equal to greater than or equal to 3. Or say it start from 3, 4, 5, 6 and so on. These are the running state. Spectral lines start from 3D, 4D, 5D, 6D, and it ends on lower state, and that lower state is 3p state, and therefore that series becomes a diffuse series. Similarly, fundamental series. Fundamental series, we write the symbol F for that one. Hence, all running state start from F state. Now, where we start the F series? When n is greater than or equal to 4, means n start from 4, 5, 6 and so on. We cannot write the 3 since 3f is not available. Is it correct? Hence we start from n equal to 4, 4f, 5f, 6f. The transition takes place from this state and ends on lower fixed state. Lower fixed state is 3d. Hence the resulting series becomes a fundamental series. Similarly, for another alkali element, that is the lithium, we also show the spectral lines and how the spectral lines arises. Hence, firstly we write the configuration for the lithium. Since we know that the atomic number for the lithium is 3, therefore what is the configuration? 1s2, 2s1. Hence the configuration is ns1, where n is 2. Is correct. Hence for the lithium, n is equal to 2. Configuration is ns1. These are the valence electron configuration, and that electron responsible for these 4 series of the spectral lines when it transit from all s states, all p states, all d states and all f states, and ends on the lower states. And which is the lower state? That we find here. Now see, this is the ground state. This is the ground state. Means which are the excited states? Which are the excited states? Excited states are 1s2, 2s2, 2p, 3s, 3p, 4s, 3d, 4p, 4d, 4f, 5s and so on. These are the excited states here. Now we know the what is ground state. This is the ground state and excited states are known. Then how we find the sharp series? Sharp series means all states are coming from S state. Which are the S states? S states 3s, 4s, 5s, 6s and so on, and ends on lower state. Lower state is which one? This is the lower state, 2p. Hence we write start from n equal to 3, 4, 5, 6 and so on. We get the resulting series is sharp series for lithium atom. Principal series. All running states are from p state. Now which are the excited state? 2p, 3p, 4p, 5p and so on. Hence we write 3, 4, 5 and so on. The transition takes place from these states, p states, to nearest lower fixed state. Which is the lower? Below 2p, here is 2s. Hence we write the 2s is the lower fixed state. Resulting series becomes a principal series. Similarly for diffuse series, all states transition takes place from 3d, 4d, 5d and so on, and it ends on lower fixed state. Lower fixed state is 2p. Hence 2p is the lower fixed state since all are the excited states here. Resulting series becomes a diffuse series. Similarly fundamental series, all running states coming from F states means 4f, 5F, 6F, and so on, and it ends on lower fixed state 3D. The resulting series becomes a fundamental series. Now these are the four groups of the series, or the four series of the spectral lines. That analysis was done by the Rydberg from the experimental observation of the alkali spectra, and we get four series. That four series, how we get these spectral lines, that we know here. Then we draw the picture of these spectral lines, series of the spectral lines in case of the sodium. That part we discuss in the next lecture. Thank you.